Welcome to this presentation on bumpless control through PID. We will discretize standard PID controller. We will assume that there is communication error, and then we will show how bumpless control law comes into place and how it is useful. Here is the standard 2-DOF controller we studied. This is the standard PID control law, which is what we will arrive in 2-DOF if we substitute Tc equals Sc. We will make the following approximations. We will use trapezoidal approximation for integral mode, and for derivative mode we will use backward difference. Let us substitute here. So k into 1 remains the same. Because this is integral mode, we will use the trapezoidal approximation. So we got this. For the third term, in the place of s, we have to put this, okay, and then E of z. So here is the approximation. Let us start with this. Let us cross multiply. When I cross multiply, I will have z into z here, z squared in the denominator. When it goes here, it will be z squared into u of z, and when I invert it, I will have u of n plus 2. You can show that this equation becomes this. You cross multiply, take inverse z transform, you should arrive at this expression. I would want you to work it out, make sure you get this expression, and if you do it properly, you will find S0 to be of this form. Similarly, you will arrive at expressions for S1 and S2. You can simplify this further, shift by 2 time units, you get un minus un minus 1. Wherever n appears, you substitute n minus 2, so you will get this expression. On the left hand side, I have it as un minus un minus 1. On the right hand side, I have n minus 1 and n minus 2. On the left hand side, you have to remember the previous value of u. On the right hand side, you have to remember 2 previous errors given by E n minus 1 and E n minus 2. Now we will discuss the preferable form of control law. Here is the control law that we derived in the previous slide. I have this question: should we calculate this as delta un equals f of this, or un equals g of some other function g of un minus 1 as well? What is the difference between these two? Here I do not care about what un minus 1 is, I am calculating delta un. So when it is implemented, this control law will say from wherever you are, move it by delta u, whereas this alternate form says go to this absolute value. These two should be identical provided you know this u of n minus 1, but there are occasions when u of n minus 1 is not known exactly. This could happen when you go from manual to automatic mode change. Initially there is no controller, people try it out manually, and before they go to automatic mode, that is feedback control mode, before closing the loop, they have to enter the value. This is where the controller is. Okay, suppose there is a mistake in punching the values. Suppose that the controller thinks that the valve position is at 5%, but the actual control valve is not at 5%, but actually at 50%, and it is working fine. Suppose the control law now gives delta u equals 0.1%. The first control law, which is delta u, it just says move by 0.1%. So 50.1% will get implemented. It will go from 50% to 50.1%, the valve. Whereas the second control law, because it gives it in absolute value, it will ask the valve to go to 5.1%. It thinks that the valve is at 5%, move it by 0.1%, it says go to 5.1%. This introduces a large bump because previously the control valve is at 50%. Now the control law is saying go to 5.1. There is a major change. Because control law is given in terms of delta U, the mismatch between what the actual value is and what the controller thinks will not matter. Hence, giving it in the form of delta U is known as bumpless transfer. This is extremely important in practical controller implementation. So, whenever possible you have to give it in the form of delta U. With this we have come to the end of this presentation. Thanks for joining. Goodbye.